Hi everybody. In this video we're going to practice finding the direction of the magnetic field at the center of a current loop. So first I just want to remind everybody that the origin of all of this is the Biot-Savart Law. From the Biot-Savart Law we can find a special expression for the magnetic field at the center of a current loop that has this magnitude, mu naught I over 2r, where r is the radius of the loop and mu naught is a physical constant and I is the current in the loop. That gives you the magnitude of the magnetic field at the center of the loop, and it's only the center of the loop. It's not here, here, here. It's at the center of the loop. The direction we can find through either a special derived right-hand rule for current loops, or we could go back to the derived right-hand rule for the magnetic field due to a current segment. All right? So in this example, or this problem, I just want you to find the direction of the magnetic field only at the center of this loop and at the center of this loop. So pause the video, take a minute to do that, and then restart the video and I'll go over the answer. Okay, we're back. So using the derived right-hand rule for a current loop, we stick, using our right hand, we curl our fingers in the direction of the sense of the current in the current loop, and our thumb will point in the direction of the magnetic field at the center of the current loop. So my thumb is pointing out. That means the direction of the magnetic field here is out. That's the direction of the magnetic field. Now I could have done this another way. I could just pick a representative current segment. Oh, how about right here? So imagine right here. If the current's going this way, then right here the current will be going in a direction tangent to the circle. I could draw myself a little r perpendicular from there to where I want to know the magnetic field and its direction. Then I could stick my thumb in the direction of the current segment. My fingers would wrap around, and at the center of the loop, my fingers are coming out. So it's consistent with that. And you could put other representative current segments anywhere. I'll do one more. How about right here? Current would be in this direction because it's going to be tangent to the circle. Draw myself a little r perpendicular. Stick my thumb in the direction of the current, my fingers would wrap around, and they'd be out. So that's all consistent. I'll just label that as a direction of the current. Little bitty current segment there, little bitty current segment there. All right. Now let's do this one. Now you imagine, well, if the current here is going opposite the direction of the current here, we should probably get a result that's into the board. But let's check that. Using the first derived right-hand rule for current loops, put my fingers of my right hand, curl them into the sense of the direction that the current is sort of circling, and my thumb will point in the direction of the magnetic field at the center of the loop. So the magnetic field at the center of the loop is into the board. Now I could pick a couple representative current segments. How about one right here? So imagine a little current segment right there. If the current's going this way, then the current at this current segment is that way. Draw myself a little r perpendicular. And sticking my thumb in the direction of that current segment, using the right-hand rule for a direction of magnetic fields due to current segments. Thumb in the direction of the current segment, fingers wrap around, and my fingers are going into the board, consistent with the right-hand rule that I used for, especially for loops. Okay, so for loops, it's pretty simple. If you're looking at a loop face on, the magnetic field is either going to be out or in, and so these right-hand rules will help you know which direction you have. Again, if you want to find the magnitude of the magnetic field at the center of a current loop, you need the radius of the loop, you need the current in the loop, you need the value of this physical constant. And again, keep in mind this formula is only good at the center of a current loop. All right, thanks for watching.